Good afternoon, everybody. You can see we're going to be learning about limiting and excess reactants. I've started out by writing down a few notes, 5 total notes about limiting reactants and excess reactants. In just a minute, you can hit pause and you can write these down. Okay, go ahead and hit pause. I want us to think about an analogy first, and I'm going to call this the backyard barbecue analogy. All right, in this analogy, you're going to have a backyard barbecue for you and your friends. And at this barbecue, you're going to make hamburgers for everybody. Now, our recipe for hamburgers is going to be one bun, and a bun is defined as a top and a bottom to the bun. So one bun plus one hamburger patty is going to make one hamburger. All right, now one of your friends brings over the buns, and your friend brings 100 buns. This is going to be a huge blowout. It's going to be awesome. Your other friend brings the patties, and he brings one patty. The question is, how many hamburgers can you make for you and your friends? Now the answer is obvious. Because you've only got one patty, and it takes one patty to make one hamburger, you can obviously only make one hamburger. And the reason is because you run out of patties. You run out of patties, and that causes the production of hamburgers to stop. For this reason, the patties are the limiting component. You could call it the limiting ingredient. You could also do a little bit of mental math, and you could figure out that, well, you ran out of the patties, but you've got extra or excess buns left over. We have leftover excess buns at the end of this, and in particular, because we used one bun, we have 99 buns left over. We're going to keep going back to that backyard barbecue analogy as we solve the stoichiometric problem that's down below here. All right, first thing I'm going to do is to emphasize a couple of problem-solving strategies as we read this example. Now, these are recycling of problem-solving strategies that we've used in the past. All right, start by reading the question. It says, if you begin with 10 grams of sodium. Remember, when you read a given number, unit, and chemical, you immediately drop down to the balanced equation and circle the chemical and the coefficient. So 10 grams of sodium and 10 grams of diatomic chlorine gas. Circle the chemical and the coefficient. The question asks, then what mass of sodium chloride will be produced? Circle the chemical and the coefficient. We have to do two strings of stoichiometric conversions. First, going from sodium to sodium chloride, and second, going from diatomic chlorine also to sodium chloride so that we can make an apples-to-apples comparison. Now, I'm going to define this bottom arrow right here, going from sodium to sodium chloride, as mathematical string of equations 1, and I'll put that right down here. This one is going to be 2. 2. All right, emphasizing another problem-solving strategy, we start initially with 10, this is in number 1, with 10 grams of sodium. This would be grams of A. And we're asked to convert to grams of some other chemical, mass of some other chemical. So this is a gram A to gram B conversion. And remember, you have to use a series of 3 fractions to get from grams A to gram B. So I'm going to put gram NaCl at the end. Okay, that's string 1. String 2 right here, we're going from 10 grams of Cl2. We're doing a gram A to gram B conversion, ending also at grams NaCl. Okay, at this point in the course, I expect that students are good with the stoichiometry. So I've written out the stoichiometry. We just need to fill in the numbers in each one of these spots. This is the molar mass of chemical A, which is sodium. The molar mass of sodium is 22.98. That comes directly from the periodic table. So right here we need the mole ratio of sodium to sodium chloride, but because we've used this problem-solving strategy right up here, we can see that there's a 2 to 2 mole ratio because the coefficients in front of each chemical is a 2. Down here we need the molar mass of sodium chloride. To calculate the molar mass of sodium chloride, I'm just going to make a little accounting table up here. Sodium is 22.98. Chlorine is 35.45. I take the sum of those mass numbers. Take the sum of the mass numbers, and I get a final molar mass of 58.43 grams per mole. So this is 58.43. So now it's the same statement about calculator use that we always talk about. We multiply across the top and divide by everything on the bottom. Don't forget to tell the calculator that both of these two terms are on bottom. Okay, so the way that I like to do that is 10 times 2 times 58.43. And then, of course, we do divided by parentheses, 22.98 times 2, close the parentheses. And we get this potential answer right here, we'll say 25.43. All right, so now we're going to move on to the second string of calculations. In the second string of calculations, remember, we're going from 10 grams of diatomic chlorine to some potential mass of sodium chloride that we might be able to make. So I've already set this up down here. The molar mass of an individual chlorine is 35.45, so when we double that, we get a molar mass for diatomic chlorine of 70.9. The mole ratio of chlorine to sodium chloride is 1 mole of chlorine per 2 moles of sodium chloride. And we've already calculated the molar mass for sodium chloride. It's 58.43. Okay, so now again we multiply across the top and divide by everything that's on the bottom. So we have 10 times 2 times 58.43 divided by 70.9, and we get a final answer of about 16.48. And that's grams of NaCl. Now when I'm doing this work, I actually like to put question marks around each of these potential answers. And I want to go back, in order to explain this, to the backyard barbecue analogy. So remember, in the backyard barbecue analogy, you have 100 hamburger buns and you have one patty. Since you've got 100 hamburger buns, you might think, well, maybe I can make 100 hamburgers. Since you've got one patty, you might think, well, maybe I can make one hamburger. You make a comparison between the bigger number and the smaller number. In the analogy, it would be 100 hamburgers or potentially one hamburger. And you always go with the smaller quantity. This is the actual quantity of sodium chloride that we can really make. So before we go any further, I want to use another problem-solving strategy. I'd like to draw an arrow here and write compare. Okay, just explain that when we make that comparison, we're always looking for the smaller quantity that's right here in this case. I'm going to round this to 3 significant figures, and the final answer is 16.5 grams of sodium chloride. Once you've figured out how many grams of sodium chloride you can produce, or grams of product you can produce, I've got a little table that's down here, and you can fill this in to help you to wrap your mind around what's going on in this problem. So the mass of product that's produced is 16.5 grams of sodium chloride. You find the smaller of the two quantities, this one, and you trace it backwards, and it points to the reactant that you run out of. We only have enough diatomic chlorine to make 16.5 grams of sodium chloride, and once we've made 16.5 grams of sodium chloride, we run out of diatomic chlorine. For that reason, the limiting reactant is diatomic chlorine, and by default, the other reactant, Na, must be the excess reactant. So we can make 16.5 grams of sodium chloride. We run out of diatomic chlorine, and we have excess extra sodium left over at the end. Okay, this year we're not going to be working on step 3, so you don't need to worry about step 3 down there. Okay, and that's how we do limiting and excess reactant problems. All right, thanks guys, and I'll see you soon.